Okay, so hello everyone. So very welcome to our this seminar, this semester's rigorous efficient AI seminar series, and this is our first talk. And today we're very glad to have the Professor Kai Ni from the University of Notre Dame to give us this talk, high performance and secure edge computing using ferroelectronic FET. And Professor Ni is right now the assistant professor in the University of Notre Dame in the electrical engineering department, right?
Yes.
Yeah. And he has very rich experience in the semiconductor device circuits and the system designs. And he has around 200 publications in top journals and conferences, including the Natural Electronics, IEDM, VS Symposium, IPS, and so on. So very prestigious journals and conferences. And his current interest lies in the nanoelectronics devices, empowering unconventional computing, domain-specific accelerator, and the memory technology. So as you know, right? So right now, so the semiconductor industry is a very important field in this nation, and those the devices towards the future generations that is critical to secure the technical advantage of the nation. So let's welcome Professor Ni to give us this talk.
Okay. Thanks a lot, Paul, for the nice introduction. So, hello everyone. It's my great pleasure that able to present our group research to you. And my title is looking at high performance and secure edge computing using ferroelectric transistor. We call it ferroelectric FET or FET. All right. For those who have not been to Notre Dame before, this is our campus. All right. If you look top down, it's pretty beautiful campus. Happy to visit, and I can show you around. Okay, if you have happen to be around. Okay, so Bo, I don't know how the format is going to look like, but if you have questions, feel free to interrupt. All right. And this is the outline of my presentation. I'll first give you a background on this technology that we developed. It's called 1FET1C. All right. I will motivate or explain why this is interesting, especially in the context of this 1T1C DRAM, which we all are familiar with. I will talk about the opportunities of these technologies, and then I'll show a few examples. Okay, what this technology can enable us. Mainly in the compute and also security side. We're looking at this, of course, matrix vector multiplication with the binary multi-bit weight. Also talk about this content addressable memory, and also this physical unclonable function. And in the last, I will show some of the work that my colleague did here. He's using the dual mode for 1FET1C and able to map some of the transformer workload to this technology. And then I will conclude. All right. All right, let's get started. Okay. I think for this audience, right, it's all energy efficient AI, right? So I think this is not strange to you that we have this memory wall problem, right? As summarized in this paper, you can see that computing hardware, that computing performance like flops, right? There's a like it grows at a pretty fast speed, like doubles every, not doubles, like triples every 2 years. But on the other hand, the memory cannot grow so fast. Okay, the speed, the bandwidth is not growing very fast. Part of the reason is due to this I/O. The I/O cannot grow very fast. There's some like a physical channel. It just cannot increase very dramatically. And part of the reason is the memory architecture. It's not suited for the very high bandwidth that nowadays for AI, right? High bandwidth memory is definitely very hot. It's trying to address this problem by using a lot of wide parallel IOs. But even that is now we are entering this kind of like conventional growth of the bandwidth in HBM. And now it's like 1.6 I think it's about a 1.6x improvement every 2 years. So we have a huge gap. Compute grows so fast, and data it cannot be supplied enough speed. So we are really bounded by this bandwidth. Okay, so that is kind of like the bigger motivation actually for all the memory technology development. How can we make it faster? There's huge interest, all right? How can we make the DRAM better, right? In the past, right? In order that we have this von Neumann architecture, right? We have memory compute, and then there's a very narrow bottleneck between them, and data has to be transferred between them. And we know this is challenges, right? And that is where all this bandwidth bottleneck come from. So of course, the people start to look at, all right, can we just now make the data and the compute closer, right? Generally, people call that like processing in memory. So there's a lot of early research people already did, like they call processing using DRAM, right? What you're doing is basically without changing the DRAM memory, can we do this, implement some logic behind it? For example, you can copy one row to another row using just intrinsic memory operation, or you can implement some kind of majority gate, or that you can implement AND or even NOT logic. So by doing that, you're just trying to implement some kind of like a logic inside it, right? Also, people look at using lookup table, but this is quite limited. All right, there's only certain logic you can implement, and moving also further is that people also start to also look at can we just okay, I don't want to activate multiple rows at the same time. What I want is just bring my compute and logic and memory closer together. That's what they're doing. I implement some kind of logic, including AND and adder tree, so that I just bring the data into the logic and do compute. And this approach is widely embraced by the industry. Like there's multiple startups companies like UPMem or D-Matrix recently announced. And of course, there's memory vendors like Samsung, SK, and Hynix. They all have their own product. And this is pretty promising, right? So this kind of like three are all already commercialized or on the horizon. But if you look at the DRAM, right, one thing that is missing is this analog computing memory. We know that if we can activate massively parallel fashion, all right, and if you do this analog summation, then you have the maximum bandwidth, all right? And this way, you're relying on the parallel activation. Analog summation is difficult in DRAM. Why is difficult? We want to look at this, all right? Why is difficult? The main problem is that all your information is stored in the DRAM capacitor. And we know that why DRAM is called DRAM, because the charge will leak away, right? That is first challenge. The second is that if you massively, like parallelly activate the whole array, all right, every time you read it, you destroy the DRAM information. So if you have a whole array activated, then your whole array's information will be gone, all right? Then you have to reload the same information to it. And that defies all the purpose of doing this computing memory. So this is not very attractive, all right? Then how can we solve this problem, right? So me as a device engineer, we have all the tools available, and we can create different technologies that is probably not available right now. So that is a great advantage of us. So we were thinking, all right, what if you make the access transistor to be non-volatile, all right, so that it can store, let's say, two memory state, like a 0, 1. Then I can store my weight in this non-volatile memory, and this capacitor, all right, it will be just used for computing. Then if you do that, all right, then you can sense this line, all right, this line voltage as analog summation or matrix, weight matrix multiplied by the input on the gate, all right? So if we have this kind of technology, then I can do this parallel activation and do this analog summation to maximize this bandwidth, all right? So that is kind of like what do we want to do? Then the question is that how do we realize that, all right? To be able to explain to you, you may not see this material very often, so I would like to give a very short, brief introduction to Ferroelectric, all right? So the transistor we want to build is Ferroelectric field effect transistor. Then what is ferroelectric, all right? So ferroelectric has been around for a century now. It's very old it's very old material, all right? So essentially what it does is that this shows the atomic structure, all right? For a very old ferroelectric, we call perovskite. What it does is that you have this positive charge and negative charge that are displaced from each other. Typical material, the charge overlap, all right? So you have a net zero, we call it dipoles. But if you have a positive and negative charge that displace from each other, then you have remnant dipoles. And that remnant dipoles, okay, for example, shown here, you have this kind of like a positive atoms, or kind of like this blue one, all right? It's displaced from the center. This red atoms, the oxygen atoms, the negative atom. So their center is here, okay? Charge center is displaced from the blue one. And this blue atom position actually can be flipped by electric field. So if you apply electric field, you could flip him back and forth, all right? If you look from sideways, this is what it look like. You could have oxygen atoms here, okay? The center of the negative charge, it would be really the center. But the blue atom could be up or down. And that up or down store 1 bit of information, and that can be switched by electric field, all right? And this has been around for a long time. It's not exciting the community, not exciting the community. But then in 2011, that new breakthrough comes in, that people discover for electricity in hafnium oxide. That's really a big breakthrough, all right? And here shows the atomic structure of this. And basically, in hafnium oxide is you have this look at this very dark red oxygen atoms. They can be switched the position up and down by electric field, all right? If you look at from sideways, these two oxygen atoms, all right, they can be flipped by electric field up and down, all right? So this simple animation shows you, all right, how you can flip the atom positions, and these two stable position can store 1 bit of information. That's the memory we're looking at. Okay, so why hafnium oxide brings excitement to the community, all right? Here shows the important metric we call remnant polarization. That is indication of how strong a ferroelectricity is as function of the ferroelectric film thickness, all right? The conventional perovskite I mentioned before, all right? If you try to make it thinner, all right? If we want to make a high density memory, we want to have thin film. If you make it thin, you will lose your ferroelectric, all right? That is intrinsic material property. But if you look at it for hafnium oxide, that's opposite, all right? If you make it a little bit thinner, actually you could hold your polarization, and that is game changer, all right? People now even demonstrated with 3 nanometer, you can still have ferroelectricity. So that make it ideal to make a low voltage, right? Make a high density memory, okay? So the journey of hafnium oxide started in 2011, and after that, there is a significant development in the community. Right after 1 year later, after the discovery, people already integrated this ferroelectric into a transistor in 28 nanometer technology node. And then a few years later, they did even that also for FDSOI. Okay, that's another type of platform in 22 nanometer. And fast forward in 2020, people start to look at, okay, can we stack one FET on top of another? Okay, so that I can have multiple tiers of memory for my embedded non-volatile memory for, let's say, for AI application. People already did that. And now people also looking at, can we use a FET in the vertical fashion, or can we build a solid state drive using ferroelectric? All right. And recent major milestone is demonstrated by Micron, which is a memory vendor, that they demonstrated you can stack 2 tiers of ferroelectric capacitor memory, and they demonstrated in 32 gigabit. That's really a leap forward in the community. All right, this really shows you that this type of memory is really promising. Okay, so how does this memory work? All right, I'll give you a short introduction. I'm saying already now you can flip the atom position. All right, what you can do is apply electrical pulses to it. And this shows the standard ferroelectric QV hysteresis loop, we call it. All right. Well, how do you understand that? Let's say you're starting from here. It could be -2 volt. You increase the voltage, you will then follow this loop. The chart will increase like this. And then when you go back from 2 volt to -2 volt, all right, you're going in reverse. And then you're following another loop, another path. We call this a hysteresis. Then you will see at 0 voltage, right? You have a different correlation that corresponding to 1 bit of information. Okay, and that is we call it metal ferroelectric metal capacitor. Another type of ferroelectric memory, which we are interested, is if we insert the ferroelectric into a MOSFET gate stack. All right, you put the polarization either up or down. Okay, you can use the gate voltage to set the polarization state. If the polarization pointing up, you will get IDVG curve with high threshold voltage. If you apply positive pulse, then your threshold voltage will reduce. Okay, so this means that if you now you can simply read out the channel current, drain current. You can find out whether it's low current or high current. Then that corresponding to your memory state. Okay, and that is very attractive because it's single transistor memory, and also you see you only apply the pulse on the gate. Gate is insulating, so it's not consuming power consumption as well. So that makes this like ferroelectric transistor memory highly attractive for embedded non-volatile memory applications. And also the ferroelectric FET is highly scalable with hafnium oxide. All right, here shows the device gate length. Okay, is a MOSFET gate length is indication of how small you can go. Right, it shows as function of publication year. You see in the old perovskite days, okay, you're limited by at least 100 nanometer gate length. You cannot just break through it. Then when we have ferroelectric hafnium oxide discovered, okay, with silicon substrate, we are already approaching the logic design rules, which is pretty good, all right? And then if you have this back-end line 3D integrated memory, we can even approaching 10 nanometer, sub 10 nanometer gate length. That's really small. Okay, so this also shows you why this is interesting. Then I would like to also show you a simple comparison of different type of non-volatile memory, right, to give you a better context. All right, if you look at like an embedded flash, STT-MRAM, magnetic memory, 1T1C ferroelectric, or phase change memory or resistive memory, FET only have one transistor. It's very compact. All right. And is sensing, all right, the on-state and off-state. For FET, we can easily have more than 10,000 on-off ratio. So that's really make it sensing very easy. And also, when you read it, it's non-destructive. You can keep reading it without having to write it back. Remember, DRAM is destructive sensing, okay? And it's the right voltage. It can be made less than 4 volt. Recent breakthrough people show even can work with 1 volt. So that's another important thing. Another thing is that its write energy is very energy efficient. Like I said, you apply pulse only on the gate. It's insulating. You're consuming around 10 femtojoule per bit. So that's really efficient. And write speed is also fast, like around 10 nanoseconds. Write endurance is not as impressive as the other metrics, but we're still able to get like 1 million to 10 to the 10 cycles. Okay, so overall, FET is a pretty good, promising technology platform. All right. So now we have this non-volatile ferroelectric, okay, available as our design tools. Then we can re-examine this 1T1C type, almost like DRAM cells, right? So if you look at this axis, depending on whether the access transistor or capacitor, all right, we can have conventionally DRAM 1T1C, all right. Capacitor is now volatile, transistor is volatile. Or you can have a non-volatile capacitor. We call it the FERAM, okay. This memory is what Micron demonstrated in their 2 tiers. The next one is this 1 ferrofluency, where we're using non-volatile access transistor and volatile capacitor, all right? And of course, the last one is just both of the transistor and capacitor are non-volatile. And this is the one we are interested in this talk. I will show you why this is interesting. If you look at, okay, this different cell technology in doing this computing memory, all right, we have this DRAM, all right. As I mentioned before, DRAM problem is that first you have to refresh, okay. Second is that it's destructive sensing. So you have to load all the array after you do the compute. That is just not attractive. All right. Or you can, if you want, you can use the 1T1 ferrocap. All right. But ferrocap is also destructive read. It has the same problem as the DRAM. All right. So that's also not a very attractive. The third option is this one FET 1C, which we think is very promising, is that if we use this FET, which can store the weight, all right, which is non-volatile, you don't have to refresh, and then you can use this capacitor, okay, to do the compute. Now the capacitor don't hold information; it only holds temporary computing results. I'll show you how you can do that. Right? In this case, you do not need to copy or you do not need to write back. You do not need refresh. And you can even also suppress the FET variation. It has all the nice properties. The last one is the one FET 1 MFM. This one is not explored much, so we're not going to focus this in this presentation. All right. So if you compare, all right, these 4 different categories, okay, this is their cell structure. The one for 1C, okay, we are not changing the capacitor at all so that we can leverage this DRAM processing. Okay, engineering the capacitor is very difficult, all right? Even though it's just a metal, insulator metal, it's very difficult in DRAM industry, all right? So we're not touching that, okay? All we did is just we replacing this excess transistor dielectric with ferroelectric, all right? We think that's a minimal disruption. And now in polarization stores the information. It's not like DRAM, the capacitor charge. And now the capacitor role, in our case, we only use that for compute. We're not storing information. So we don't have to worry about refresh. We don't have to worry about this destructive sensing. And because it's only used for compute, we don't need a very long retention for the capacitor. And we don't need to write back. Okay, and the endurance now is almost like DRAM because it's just DRAM capacitor. So overall, we think this one for fluency is really nice for this compute applications. So not only that, all right. If I don't know how much you know about DRAM, DRAM now is really the transition point where we are seeing significant investment in this. All right, we all know this HBM, right? We use stacking multiple chips and through using through silicon via. But what is beyond DRAM, right? Industry is going to this what we call 4F square gate all around DRAM, where you're using this vertical transistor as the 1T1C. Okay, then you can save the DRAM area. And beyond that, we are also replacing silicon channel with another type of material. And this material has ultra low leakage so that you can have DRAM like now can hold even up to hundreds of seconds, thousands of seconds, make DRAM almost non-volatile. So that's also very exciting development. Okay. And what's even more exciting is this monolithic 3D DRAM. You know, DRAM is all planar memory. And our solid state drive is 3D. So we are also looking at DRAM now at the inflection point that we're going to 3D. So imagine later in the future, you could have hundreds of layers stacked DRAM. You could have a gigabyte DRAM. Terabyte DRAM. So that would be very exciting. Okay. And if we, this is for silicon channel, and if we use another oxide, we call it oxide channel, you can even have a very long retention 3D stacked DRAM. So all of this, okay, this one FET 1C can leverage the DRAM investment and knowledge. So we believe we can use the one FET 1C in this array architecture as well. All right. So have done a long introduction to you about why one FET 1C is exciting. Hopefully we're on the same page, why that is useful and why that is promising. Okay. Next section, we'll just delve a little bit deeper into what you can do with DRAM. Now with this one FET 1C. Okay. We're starting with simple matrix vector multiplication. All right. But before we do that, all right, we have been motivating from 1T1C side, all right? Yes, one FET 1C makes sense. People may argue, why don't you just get rid of C? If you have non-volatile memory, you can just use the like array of the ferrofet and you adding this column current, and then you can do the analog summation, right? That is valid. Okay, that's good question. But the problem, okay, with this is that each ferrofet, okay, you're storing the weight as a channel conductance. In order to map the weight accurately, you need pretty accurate conductance. And that is a challenge for all this kind of emerging memory, because if you rely on the analog property, having very precise control of your channel conductance is not easy. As a result, if you do the analog summation, you're going to see a large spread of the computing results, and that increase the error rate for your computing. But this with 131C, we change the picture, all right? We change the story completely. In this case, we're storing the weight as the on and off state of FET. It's not the exact value of your channel conductance. Right now, I'm just leveraging FET as a non-volatile switch, whether it's going to be charging the capacitor or not charging the capacitor. So that is itself is very robust, right? If you FET turns on, whether it is conductance is 10 or 11, it doesn't matter, right? So I can still just charge up the capacitor to whatever voltage I supplied. Then by doing that, this cell is very robust and very error tolerant, okay? So we should be able to see much smaller error rate. I'll show you that later, okay? So overall, we think this charge domain computing using 144NC is a way to go. All right, so let me briefly show you how does it work. Here I show all four different combinations, okay? Depending on what you store, whether it's 1 or 0. 1 will be low VT state, okay? 0 will be high VT state. And then your input, all right? The input binary, you can be supplied on the gate of the transistor, okay? And you can clearly see, all right? If you're supplying the bit line with working voltage, let's say 0.5 volt, then only the cell, right, storing weight 1 and have input 1, because you have input 1 is here. If you input 0, all the transistors are cut off. If you input 1, then the low VT state device will be conducting. If it is conducting, then you will charge up this bit line voltage to the cell capacitor, right? And all the other cases, you will be grounded, okay? You'll not be able to charge it. So this implement a simple AND operation, basically binary multiplication, right? After you're charging it up, then what you can do is just you turn on all the transistors, okay? Turn on all the transistors and performing charge sharing. Charge sharing basically the end is a summation operation. Then you can sum up all the capacitor node voltage, and this is and at the end your bit line voltage, okay, is this equation. And you can clearly see that there's a multiplication, matrix multiplication, matrix vector multiplication embedded there. So it's very simple charging step, and then you do computing. All right. We are a device group, so we have to do experimental demonstration. So we are basically fabricating our device. All right, this is all done at the Nordam clean room. We can build all this kind of device using one transistor, as shown here, and one capacitor. I'm not going to go to the details of the process. Okay, yeah, anyone interested, definitely be happy to go over that. And here it shows the device characteristic. Okay, here we are showing kind of like a 2-bit storage. You definitely see the low VT state, IDVG, and you also see high VT state. And you can just change in your program voltage. You can reach also intermediate state. All right. On the left shows the speed, how fast you can write it. Okay. If you look at here, with given high enough voltage, you can program even below like 100 nanoseconds. This is limited by our instrument. Okay. So the first thing we did, okay, you can easily charge up this capacitor. We're validating whether we can either charge or block. Okay. So for example, we program the device, and then we're applying this read voltage that is between the low VT and high VT. If it is low VT, the cell will be conducting. So you can see we apply 0.5 volt, it's charged up to 0.5 volt on the capacitor. So that makes sense. But if it is you have high VT state, all right, your VTH is high, your read voltage is not turned on the transistor, so you cannot charge up the capacitor. In that case, you see the voltage is not changing, right? So you can have precise control of the capacitor voltage, and that is depending on your applied voltage and also your stored voltage. Okay, and that validate a single cell AND operation. We also did have multiple 6 cells connecting in parallel, and we basically charging up the capacitor and do the analog summation on the bit line. And this you can see here for different theoretical output, right? We're seeing that bit line voltage is at different voltage. And if you extract the bit line voltage as function of theoretical output, you see a linear relationship as what we expected. One thing is that in our university clean room or lab, it's hard to build a very large array. So sometimes you see a very small array demonstration as a proof of concept. But definitely we're moving towards larger scale integration and building up the capability to measure, test larger arrays. Okay, but this shows you a proof of concept. All right. And we're also using SPICE simulation projecting, okay, with the device model. We're showing the output as function of 64 cells, all right? And we're adding the FET, the device variation into it, all right? So on the left side is the conventional computing, all right, with summing up the column current, just using FET array. And you clearly see if your device variability increases, right, your output results will significantly deviate from the linear line, right? You're seeing a large spread that's due to the device variation. However, with our 151C, you clearly see with the same amount of variability, our result is pretty clean, all right? That's because we're using FET, as I said, only as a switch, all right? We're not care about too much about the exact value of your connectance. So this is pretty convincing, okay? We also evaluate it, all right? What if our capacitor also have variation? So we add 0 all the way to 5%, and you can clearly see, we kind of zoom in somewhere around here. You can still distinguish between the neighboring levels, all right? That definitely shows this robustness of this 151C, okay? Next, sometimes, right, so far we have been talking all about the binary weight. So what if your weight is a multi-bit, right? If you have 4 levels, not 2 levels, right? Can you still do it? We're showing that we can by using this multi-step charging and discharging, all right? What do we do is that every time, each step, you're just charging to different bit line voltage, either 1/3, 2/3, or like complete voltage. We apply this on the bit line, all right, and then the capacitor will be charging to its corresponding weight. Okay, if the weight is 1/0, then it's going to be charged to 2/3. If it is 1/1, it's going to charge to the whole voltage. If it is older than 0/1, it's going to charge to 1/3. In that way, you are able to charge up the node, the capacitor, corresponding to its weight. Okay. Then at the end, you also have this equation here. But now the weight is a multi-bit. It's not just binary. And in this case, we're still exploiting that FET acting as a switch. All right. Because each step we are using different read voltages, and we are still using FET as a switch, whether it's on or off. Okay, we still retain our robustness against the variation. You can convince yourself, all right? You look at it, it does the work. I'm not able to go to the too much details of how array actually work. And we also build, okay, that's a nice thing we have as device group. We can build all kinds of testing structures that we want. And we actually only have 4 due to our testing limitation. And this is our testing array, and this is our transient waveform we applied. And here definitely it shows you that how the charging happens. Okay, you see, like if your weight is 0, 0, the charge doesn't change. But if your weight is 0, 1, 1, 0, 1, 1, you clearly see that your capacitor is charged to different value corresponding to its weight. All right. And then the last step, when we do the charge sensing or charge sharing step to do analog summation, and you can see there's a linear relationship as what we expected. Okay, this shows you this multi-bit that we can do both multi-bit and also single bit operation for the matrix vector multiplication. Next part I would like to briefly mention is another macro that we developed is content addressable memory. All right. For those who are not very familiar with what this is, if you, for example, you want to compare, all right, you have something you want to compare. If the memory stores something similar, what you have to do if you only have conventional memory, then you have to transfer all the data from the memory out, right? And you have to compare your query data, and you have to do XOR, whether it's match or doesn't match. In this, you do have to transfer all the data, and then you consume a lot of bandwidth, right? And in contrast, this content addressable memory, what it does, it directly compare the content of your query with each row of data automatically inside the memory. Then you do not need to transfer the data out. It automatically does this computation inside. And this functionality is very attractive for many AI applications nowadays, because you have to find your closest one, right? Find your nearest neighbor, something like that. So we're also interested in this kind of macro. It turns out that you can also do that with this one frequency. Here it shows again this binary state. All right, what you do, right? First, you have to do two-step charging, discharging. The first step, what you do, you are applying this. First, you're applying the surge voltage on the gate. Okay, this is a surge information, and you store your information into FET threshold voltage state. And first thing you did, okay, I'm gonna find out if I store 1, but I search 0, okay, the mismatch. All right, if you do XOR, that should give you a 1, right? So what do we do is that first step, I'm finding out this kind of mismatch. Okay, by doing that, you can see if you're storing 1, right? But you search 0, okay, this transistor will be cut off. So if it cut off, all right, you're not able to charge it. And all the other caps will be conducting. They will be charged, all right? So first step, you find out the caps. I find out the mismatch cases, okay? When you search 0 and store 1. In the second step, you're finding another type of mismatch where you store 0. Actually, you stored 0, but you're searching 1, right? If you search 1, all right, in this case, you search 1 and you store 0, this cell can be conducting, all right? And previously it's charged up, but now the second step, it discharges, all right? So by doing this two-step charging, you're able to find both mismatches, store 0, search 1, or store 1, search 0. So only those capacitors will be at ground, and all the other match cases, they'll be fully charged. All right. So you're able to find out those cells with this two-step operation. And the last step, of course, is to just do the charge sharing, and then you are able to sensing the bit line voltage. That's a reflection of how many mismatch you have. You know how many mismatch or how many match. That is basically Hamming distance. All right. So you're able to find out what is your stored word distance to your search word distance. And also we expanded that to also TCAM, ternary content address memory. All right, previously it's only binary CAM. You can only store binary state. For many applications, you don't care state, this X state. All right. We also proposed if you can have Ferroelectric store 3 levels, okay, and you assign the highest VT as this store don't care state, then this state, the cell will never be able to turn on. So the capacitor always stay at 0. Then they don't care. You don't care. They don't participate in charge sharing. So by simply doing that, you can realize this TCAM function. Okay. And we also experimentally validate that. All right. Here shows the sensing. Okay. Here, if you search 0, then if you store 1, that is mismatch, you got high voltage. And if you store don't care, you got 0. Store 0, that is match, also got 0. All right. And also for other cases as well. All right. If you search 1, you store 0, mismatch, you got 1. And other cases, you got low voltage. I hope this give you another macro, right? Where we can do associative search. Previously, you can do multiplication. This you can do search. All right. Now we also benchmarked this 1 for 1C cell against the other type of other type of charge domain compute. All right, we are not the first one to do charge domain compute. People also did using SRAM cell, using resistive memory, magnetic memory. People even also did FET based, but they're using 2 FET. All right, if you have 2 FET, then it's almost not compatible with DRAM, right? But with 1 FET 1C, we are compatible with DRAM, and we can leverage the DRAM decades knowledge, right? So here we show the search delay versus search energy for 64 by 64 array. Our 1 FET 1C shows a pretty good energy delay product. And also very important thing is this, because we only use one transistor, one capacitor is very small area. So it definitely shows you that you have a very high density and a very high computing performance. Okay, so that shows you the functionality and also the property. We also collaborated with the computer scientist at the UC Irvine. They did this vector-based hyperdimensional computing. So they're taking our 1 FET 1C array and use that for HGC-based reasoning task. We're using this Raven dataset, and what they do, they basically using 1 FET 1C to implement this ResNet network using this matrix vector multiplication that extract this hypervectors that indicated whether the shape, the color, position, orientation, all kind of different properties of this object, and you have them have this hypervector represent that, and then you do this HDC operation like a binding, bundling together. You create a final hypervector to representing each object. Then what they discovered that you can store those hypervectors into this 1 FET 1C again, and using is associative search capability to find the nearest neighbor. So when you have a query comes in, all right, what you do is that it goes through this. You extract its own hypervector as well, and then you have to do is you apply this query vector to this 1 FET 1C content address memory, because you can do this Hamming distance detection. Then you can find out what is the nearest neighbor for that. So taking our array macro, that including this memory core and also peripheral ADC, they're projecting that comparing with their GPU baseline, you can have up to even 1000x reduction in the energy for this ResNet 18 or ResNet 34. All right. I think another thing very impressive is this. We compare, all right, this quality loss of the network versus the Ferroelectric threshold voltage variation. And here you can see the 3 solid lines, okay? They're corresponding to the conventional charge current domain compute. You're seeing with more variation, your error or your quality significantly reduces. But if you have the over 1 FET 1C with reasonable variation, you're not seeing degradation at all, as I mentioned, showing you in the memory core before. All right. I hope this makes sense. Next part of the thing is that we also recently started to do this is that, you know, there's many interest in securing this weight of the neural network. So this is what we proposed. We want to have this encrypted computing memory array where the weight is encrypted and stored in the memory, all right? And in order to generate the encryption key, we have to have this physical unclonable function. So using that security primitive, then I can supply the key. The key go to the array. And what the array does is that we're sensing this output, all right? And previously it's just the input times the weight. But now our array, what our array can do is that I can have this ciphertext directly decrypted in the memory, okay, using memory operation. And then this decrypted weight directly multiplying my input, all right? We have developed all the operation behind it. I'm not able to go through the details, but through this 1 FET 1C, I want to convince you that we are able to finally implementing the intended operation without adding too much overhead. And this is not very strong encryption. We're just using XOR function. Yeah, so almost like one-time pad. It's not very strong, but it still can provide a certain level of security. And it can still do computing as well. So we feel this is also neat for some applications. In the past, we also did this physical and clonal function. All right, this one we're using cycle-to-cycle variation of the FET. We basically program the in this design we use two FET1C. All right, we are basically comparing the FET strengths. Okay, between two programming cycles, and depending on its strengths. All right, I'm gonna further program whether FET if depending on the strengths of the two cycles, I'm going to program one for a FET to low VT, another to high VT. This is kind of like reprogramming. Then you have much stronger tolerance against, let's say, temperature or supply voltage fluctuation. But after you do that, then you can apply challenge, a response pair. Challenge is applied to this source and drain input, and the response is generated on this capacitor top plate, and you can sense that. We also using we use a Global Foundry FET process to demonstrate the chip, and we're able to show that our intra Hamming distance is pretty reproducible, and inter Hamming distance is almost perfect as well, showing the uniqueness. All right, and also another property of our path is that it is also reconfigurable. You can reprogram, re-register the path so that every registered reconfigured path exhibit different unique response. All right. So I'm not going to go to the details. Our current design is showing that we can even use one FET1C for this purpose as well. We don't have to use two FET1C. Okay. So that kind of like concludes most of the presentation. In the last, I want to briefly mention my colleague's work because I feel this is a very interesting one. So what they discovered is that you can use a FET1C using two modes. All right. This capacitor, you can still hold information if you want to. All right. So that can work as a temporary buffer. All right. If you have intermediate results, you don't have to write FET because programming non-volatile memory is costly, right? It's expensive. And then you can use this non-volatile memory for permanent storage, like weight storage, so you don't have to change it often. So you can have this two mode, right? Then what they do is that they using this property to map the transformer workload. Basically, idea is that you store the weight in the FET, okay, like QKV, those weight matrix. You're storing those temporary results like Q times K, right? This the inner product in the capacitor temporarily, right? So by doing that, you can trade off this cost to program non-volatile memory, and it is a good hybrid solution, right? So what they did is that, okay, if you use the FET to store the weight, you can use that input come in, and you can do the matrix vector multiplication, get the QKV, all right? And if you want to do this Q dot product K, right, you store this information in the capacitor. So simple idea, but it really nicely leverage the device properties, all right? And they're taking our macro with energy latency, ADC included, and they're showing with H100 baseline, they're achieving like a 84x improvement for data center application and almost more than 100 for edge applications. All right. I know this we're not able to go to too much details, but if you're interested, we have papers published, so you can take a deeper look. All right. I think we're almost about time. So at the last, I would like to conclude my presentation. I hope through this presentation, you are able to get takeaway message is that one FET is an interesting platform. Okay, it could enable high capacity, high bandwidth, and high computing performance. All right. Regarding the capacity and bandwidth side, we want to be compatible with DRAM. So DRAM have decades-long development and also have exciting 3D DRAM architecture coming up. We believe that we can continue DRAM scaling and have very high density DRAM. All right, so we can have a pretty high density and high bandwidth for computing. And on the other side, we can also have a very high energy efficiency using the charge domain, and especially using FET as a non-volatile switch rather than very accurate channel conductance resistor. Okay, I hope this message you're able to take that message, and that concludes my presentation. Thanks for your attention. Okay.
Thank you, Kai. Thank you very much. It's a very informative presentation. And any questions from the audience? So you can either unmute yourself to ask questions, or you can input your questions in the chat box.
Yeah.
Professor?
Yes.
Thank you for your excellent presentation. I have a quick question.
Yes.
So as we all know, FET still face endurance limitation.
Mhm.
In your opinion, what are the most effective ways to improve the endurance and make FETs more ready for large-scale industrial use?
Okay. That's an expected question. I don't. I didn't realize that there is student from very deep device level. Yeah, that's a great question. Okay, that is one of the issues of FET, especially if you use a silicon channel. The problem comes from the ferroelectric and silicon interface. Okay, if you keep cycling it, it will generate a lot of defect and make the may have a poor endurance. Right. But we're also seeing a lot of exciting development. All right, people are doing optimizing the ferroelectric film, tuning this defect composition, concentration, and they're able to see in recent development like 10 to the 8, 10 to the 10 cycles. All right, so this is pretty dynamic, evolving. All right, another aspect is that a lot of work has been going to beyond silicon substrate. Like I mentioned, this spectrum blind FET, okay, where people are using, we call it the oxide channel semiconductor. With that, okay, at very low temperature deposition, you will have pretty clean interface between ferroelectric and also oxide channel. And people are showing very good endurance using that as well. So I think this endurance problem is not a fundamental limitation to FET. I think right now, from what we see, when we start to like really design the array and design the chip, its major challenges actually come from the write voltage. Okay, many of the benefits of all this computing memory could go away if your write voltage is very high, because your logic is only less than 1 volt. Then you have to have a lot of supporting circuitry to design the right driver, read driver. So they will actually, if you do the layout, they actually occupy a pretty large area compared with the core. So lowering the voltage, I think, is probably the #1 priority to really make this to be widely adopted. Again, for that, people turn to the spectrum line FET, where you can work with 1 volt. Okay, that is promised. So, so I think this is pretty dynamically evolving. I encourage you to pay attention to the recent literature in the community. I hope that answered your question. Okay.
Yes, that's very helpful. Thank you.
Okay. Yeah.
Other questions from our audience?
Yeah, boy, is this am I the only device person talking here?
Yeah. Actually, just following the questions from the last audience, I want to ask. So here you mentioned that the write endurance right now it is still kind of the not very satisfied. So I was wondering, so then whether like for the potential application, like for example in the AI domain, it is kind of be more towards for the inference and so on.
Yeah, I think so. That's what inference makes a lot of sense, right? For example, also for some application, you do need update, right? That's what for example, my colleague is trying to exploit, right? So we're trying to reduce the write to FET. So we are looking at, okay, can we have this volatile mode, right, to store those frequently updated information? We do want to try to avoid write it very often because it is expensive to do that, right?
Yeah.
Yes.
Yeah. And also I have another question. So you mentioned that you already fabricate the chip, the test chip that in the
Yes.
So I was wondering, so how about the scalability of the Ferro FET? And so right now, so to the best of your knowledge, so what is current the largest the fabrication size?
Yeah, that is a great question. Okay. Like when we in the academia design is always small, right? Because it is expensive to do that.
Yeah.
I think the biggest for FET, right? Is demonstrated by, I think it's still Global Foundry. They have 10 megabit on chip.
Okay.
That's pretty decent. Regarding Ferroelectric in general, right? The biggest excitement is this one. Okay. This is Micron's
Yeah.
design. It's a really cool TM image, right? If you look at that, it's pretty nice. And they have 32 gigabits. So
Oh, what?
it's pretty impressive.
So how
Um,
about the bandwidth?
it's slightly slower than DRAM.
That's
Okay.
okay.
They sell it as non-volatile DRAM. Their metrics is not as fast as DRAM right now. But there's also improvement, continued development there.
Oh, okay. So then actually, so my another question is quite related to this. So here I think this is 3D is kind of the it's not kind of heterogeneous integration 3D, right? It is not kind of we want to like to integrate it to like the computing die and so on, right?
Mm.
Yeah. So I
Yeah,
was thinking, so how about like the capability for the such kind of heterogeneous integration to the other component?
so you're more talking about like a HBM type, right? 2.5D packaging or even 3D hybrid bonding, those
Yeah,
technical
3D
aspects.
harmonic. Yeah. Not the kind of the monolithic 3D.
Yeah. I think those are all open, right? Right now, what the Micron try to sell is just DRAM replacement, ideally, right? Then everything else is pretty similar. For the packaging, it doesn't really matter what is actually memory die is, right? It's really built in through silicon via and all those kind of things.
Yeah,
Uh,
that want to ask whether is that kind of unique advantage or potential limitation for this device when we come in the context of the 3D or the 3.5D integration.
mhm. I do one thing I don't think has been explored much could be that is thermal stability, right? You know, DRAM, especially HBM, has thermal issue, right? But for non-volatile memory, that thermal issue would be less severe. It can hold the charge at high temperature. It's not a problem. So in that sense, I think it could be more tolerant to that if you stack them multiple layers. But I don't know for this kind of application is always used for data center type, right? Very high performance is needed. This Ferroelectric capacitor memory still have some issue to address, especially on this latency. It's not as fast as DRAM right now. It's about 2 to 3x slower.
Okay.
But the
Okay.
capacity is great.
Yeah.
And I didn't put it here. Also, there's a huge interest going beyond this type of FERAM 1T1C. We are having also 1TNC using
Oh.
one access transistor, but you have stacking a vertical multiple layers of ferrocap so that you can even have higher density, comparable to solid state drive even. That is also very exciting.
Okay. Okay, got it. Any other questions from the audience? Yeah. So actually, I have one last question. Yeah.
Yeah, no problem. Yeah,
That is a
go
little
ahead.
bit easy, a little bit wild. So because during presentation you mentioned so the device researchers actually tried the different type of the strategies of the efforts that to like for example the one like the one ferry 1T, right?
Mhm.
1F or the
Yeah.
2F1C or the you just mentioned
Yes.
5NC. So I was wondering, so is there any kind of, I know that, so because this is kind of about the physics, so we need to kind of to follow some physical principles and so on. So I was wondering, is there any kind of the more automatic way or the principle way, or like some even like we know that right now the AI is pretty hot, or some kind of data driven or the AI guided way to kind of more efficiently to explore those different potential device design space.
I see your point.
Like in the EDA, so typically we can like want to do more, all of stuff kind of more automatic.
Yes.
So we have kind of modeling because your device also have some kind of modeling. So I was wondering whether all of this can be more kind of digitalized, kind of more automatically. So then you can kind of to in parallel explore many different type of the device configuration possibilities.
Mm-hmm. I got your point, Bo. I think from the device architecture angle, it may be a little bit challenging because the available architecture, the plausible architecture is really not much. If you look at the memory history, right? Right now it just has three types of memory: SRAM, DRAM, and flash. Either you do that through sequential stacking, through this back-end line stacking, or through this 3D monolithic. It's not like a large design space, and because it's constrained by the manufacturability, by the processing, whether we can integrate that, right? Through this semiconductor processing steps. But that being said, there's a lot of things going on for this, like for a given type of device when you manufacture that. A lot of going to digital twin development for that.
Yeah,
right?
yeah, that is what I want to say. Digital twin.
Yes. There's for semiconductor processing, absolutely, that makes a lot of sense. And people are trying to do that. Actually, that CHIPS Act funded this Smart USA Institute, right? That was that are trying to do that. So I think that part makes a lot of sense. Also, another thing could be relevant is the design space exploration. Like for a given area, right? You could build a kind of like AI model. Like I can evaluate, okay, what if my design is this or that? Like you could have geometry parameters, right? You could have like electrical parameters. I think that there it could help us evaluate the array performance, right? I think there also makes a lot of sense. Processing for digital twin, like also like electrical performance digital twin, something like that, right? And also people also exploring a little bit on the material level, of course. That's like automatic experimentation. That's
science.
That's regarding the architecture, it seems is quite limited. We don't have much design space to explore.
Because due to the constraint of the fabrication and so on.
Yes. Yeah. Not all the structure can be integrated.
Oh, okay, yeah, okay.
Yes.
Okay, so okay, so
Okay.
so any other questions from our audience?
Yeah, if you're shy, don't have a question, or if you need some time to solve, you can always find me. Okay, through my email. Happy to answer any question you may have.
Okay. So if no more other questions, let's thank our speaker again. So Kai, thank you so much. So this is a very excellent talk, very informative. Yeah. So
Thank you so much.
Yeah.
Okay.
Okay.
All right. Yeah. Bye bye, everyone.
Good weekend. Thank you. Bye.